Thank you very much, Emmy, for that introduction. It's really a great pleasure to be finally talking to a Stats Society audience in person. And I'm glad that we can also do Zoom at the same time, so those of you who can't make it, can make it. I'm sad to say that Philip Stark couldn't be with us. He'll be visiting us at some point. This is a visit that's been postponed since 2020. We thought we finally had the opportunity, but unfortunately we had to postpone once more. So he will be in town at some point. I thought he might be here just in time for the election. I guess the election's not coming yet. Probably going to be towards the end of May, based on the track record so far. So as Emmy said, a lot of my work has been in genomics, but more recently I've branched out to other topics. I'm a relative newcomer to this area, and I've had the privilege of working with many collaborators. And I want to particularly thank Vanessa Teague, who's brought me into this topic. Of my collaborators here, I said I'm probably the newest. So a lot of the topics I'm going to talk about today are actually things that they've been working on before me. So really the talk today is really an exposition of this area rather than more like an academic research style seminar that's going to go in depth in a specific area. I know also that some of my colleagues who are not statisticians are listening in. So there's going to be a bit of basic stats to make sure everyone's on the same page. So bear with me, but again, hopefully this is a talk for everyone. I also want to thank two really good students who worked on projects in this area, Floyd and Calvin. Floyd's still working away on developing a method for auditing Australian elections, and some of their work may or may not feature depending on how many slides I get time to go through. So we're going to start with some background, really motivate this area, and then we'll step through with developing the methodology from very, very simple to stuff we can't do yet. So auditing elections. What are elections? In a democracy, we often think of this as the cornerstone. A democracy is the governance by the people. Elections is one of the main ways in which people have an actual explicit say in governance. So it's one of our important things that we do. I think the AEC, the Australian Electoral Commission, described our federal election as the biggest operation outside of wartime that goes on in the country. And I'm sure they're very busy right now getting ready for an event that we don't know when it's going to happen, although they probably have a decent idea based on track record. So big operation, lots of stuff to do. Things can go wrong, things that need to be checked. That's what it's all about. In Australia, we're quite fortunate that we actually do a good job of running elections. We've got lots of good processes. We make sure people vote. The fact that voting is compulsory makes a big difference. So we actually have to care to set things up so everyone actually can vote. And if you've grown up in Australia, like I have for most of my life, I've just taken this for granted. It's just that, yeah, elections happen, they work, and we trust that we get the right answer. So we're actually in quite a good position here in Australia. Not other countries are as fortunate as us. And the idea of checking the election result isn't something that's a big issue here in Australia at the moment, but it's a big issue in other places. I'll talk a little bit about some more stories from elsewhere in a minute, but as a starting point, we're okay, but there are things that we might want to think about nonetheless. Things that we do well and things that are important that not only help us have good elections, but will also help with checking things are that we use paper ballots and we have a good process for scrutineering. So pretty much every step of the process can be scrutinized by someone, and they can check and look over the shoulder of someone from the AEC, check they're doing the right job. These are things we do a good job of. And these things take time and effort, and some people might think, okay, maybe we can cut a corner here or there. Maybe we can save some money. Governments love saving money. But when you save money, you cut corners, things can fall through the gaps. So what happens is the gaps can be pretty big. So if you go to the US, for example, Philip, if he were here, he could spend a whole hour talking about all sorts of things that have gone wrong there. These are just three I cherry picked from one of his slide decks. I think he had a slide deck with like 60 different stories. I don't know how he got time to talk through them. He probably didn't. I mean, there's things like voting machines where the precision in the count like the way it's encoded in the memory isn't enough. So by the time you're counting, the count goes up, 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 and then it starts going back, back, back down because the memory overflows. There's machines that get hacked to split votes between two candidates. All of this stuff actually happens. So yeah, we need to worry about checking the results in the US, especially. And this is where a lot of the motivation for this work has come. A lot of these developments in statistical methodology have been motivated to fix these sorts of things. And a lot of these changes have come from cutting corners, and not necessarily cutting corners, but trying to improve things, but in a way that's not helpful. So especially a lot of automation and computerization has led to processes that have many more parts where things can break. So we still do a lot of our stuff on paper, which means there's fewer places where things can break. However, things do break. In New South Wales, for example, there is an electronic voting system called iVote that's being used for various elections that hasn't had a good track record. Just late last year, they used this system for local council elections. And if you saw it in the news, it became a big scandal when the system went down. A whole bunch of people couldn't vote. So a whole bunch of votes didn't get counted. And then there was a fallout with trying to work out how many races in the election were affected and whether it changed or not and so forth. And if you want to know the gory details, Vanessa Teague can tell you all about it. She got down and got into the guts to unpick what went wrong and work out what the ramifications were. A few years ago, she was also looking into that system and discovered flaws in the encryption system that was used. So her and her colleagues found those flaws. So these things happen even in Australia, unfortunately. Luckily, that's New South Wales, right? We're fine here in Victoria. We don't do any of that sort of thing. Well, think again. The Australian Senate election, which happens Australia-wide, isn't immune to this either, or isn't necessarily immune, because it is now partly computerized, partly digitized. As you might imagine, the Senate election is quite a complicated, probably the most complex election that happens. Big ballot papers, lots of ballot papers, lots of complex counting. I think it was inevitable at some point that parts of that process got digitized. So the ballot papers do get scanned at some point. They do get digitized, so we can convert the information on the paper ballot into an image and converted that into digital representation. That ultimately, the very final count, it happens on the computer. While there are counts by hand in the like first preferences, for example, the actual final count where you distribute all the preferences, that's done on a computer. So that's fine, right? Well, if you go with all the horror stories where other computerized system, which we've seen, we want to be careful and check that things are going wrong. Things aren't going wrong. And at the moment, these processes use hardware and software that's closed source, that's proprietary. So that's one aspect that we can't check completely. The process of actually using the machines, I've been told, is scrutinized to some extent, but whenever you use these sorts of machines, you can't actually scrutinize everything. You can't look inside a computer and check what's going inside the memory chips and so forth. So we want to maybe put some extra checks and balances around this to ensure that what we get out the other end is the will of the people. Scanners, benign machines, right? Well, I discovered recently that there was a series of Xerox machines that had a bug, a very unfortunate bug. So if you look here, that's a 6. If you look there, that's an 8. I might point it out on here for those listening on Zoom. Here's a 6, here's an 8. Here's a 6, here's an 8. Feed your ballot paper in, a different vote comes out. This bug, this was a software bug in their machines inside the compression algorithm they were using, which explicitly changes parts of images with other parts of images, which, how could that go wrong? This bug, from what I know, bug was live for about 8 years before it was finally patched. How many of those machines finally got patched with the patch? Well, I don't know, it's up to their owners. And what about 8 years worth of scanned material that's now in an archive? You can't use that in court anymore. So these things happen, and this is a bug that we know about. There might be others out there. And there's more stories like that I could go into, but I won't. So we don't want to take scanners at face value. We want to check that they're working. We were interested in trying to figure out how often there might be scanning errors in the Senate. Me and my colleagues did a few things. One of them was an informal experiment in the last Senate election where we actually figured out whether our own ballots that we both submitted in the election got scanned. And we can do that because the AUC publishes all of the digitized ballots. So we can actually look up and find our ballot if you make it distinguishable enough. And we found that some of our ballots did not get digitized properly at the other end. There's all sorts of juicy details like that, but I'm happy to talk to you over dinner, but I don't think I'll have time to go through today. So with these sorts of changes and knowing the context in other countries, maybe we want to be a bit more rigorous about how we check our results. In January 2018, the Australian National Audit Office, which is one of the bodies that checks things that the government is doing and recommends things, they recommended that an auditing procedure would be added in to check the Senate election results, or at least the digitization process. Fast forward a few years, just late last year, Parliament actually passed a bill, to the big surprise of Vanessa and others who've been campaigning for things like this, that actually passed a bill that would require something sort of like an audit. It's not actually a full audit in the sense that I'll talk about, but in the coming election, the AUC is going to be doing a statistical check of the accuracy of the digitization. Now, I hope they do it well. I don't know, we don't know yet what they'll do, but I'll come back to this legislation at the end because there's some interesting wording in there. So hopefully I've convinced you there's good reasons to do an audit, to do a check of the ballots that we have. We want to spot and correct errors. And in doing so, we want to improve the confidence in the results and ultimately make sure and maintain and improve trust in our electoral system. Not that we have a trust problem here, but other countries aren't quite so fortunate. So how do we do this? Audits are about checking things. There's lots of things to check. There's mundane things like, have we put the ballots, are they sealed properly? Are we signing off who opens the box and all that sort of thing? Those sort of audits, they're important. They're making sure that the ballot papers we do have, we can trust them. They're called process audits, compliance audits. Those are not the sort of things I'm going to talk about today. I instead want to talk about checking the actual results of the election. So there's looking at, if we have all these ballots, are they counted correctly to declare the correct winner? So that's called a results audit. There are different approaches to how you might do this. I'm going to focus on one in particular called a ballot polling audit, which is the simplest one, but there are others, and I may mention a few of them later, but we'll focus on the simplest one. As the name suggests, it's like doing a poll, except instead of surveying voters, we don't need to. We've already got their ballot papers, and we've done a process audit to check that we can trust them. So we just need to survey the ballots. So we just can go out and sample the ballots. So just like any other sampling study, we need to make sure we have all the prerequisites to allow us to do this. So we need to have a list of all the ballots so that we can randomize a choice. We need to be able to retrieve particular ballots once they come out in the randomization procedure. So we need to have all of those on hand. Now, not every election that happens in overseas jurisdictions has all of the infrastructure in place, but these are important to ensure the integrity of the audit. And for those of you who know about sampling, you know that there's a distinction between sampling with and without replacement. I don't want to worry too much about it. Typically we'll do without, but for the purpose of simplicity, all the equations I'm going to show you are going to assume with replacement. And typically it won't make a big difference. It's just, especially if you're doing a small sample. So let's actually do one just so that you got it in your head, what this sort of looks like. Now, I'm going to actually do this, a demo in front of you, and we need some names here. So we need to imagine we have an election of 2 people. Now, when election researchers talk about hypothetical elections, they always have pseudonyms. They traditionally used to use Alice and Bob as the 2 candidates. Unfortunately, Alice and Bob have retired as of last year. They are banned from being used, especially used in the University of Edinburgh for the purpose of diversity. Anyway, Alice and Bob, it's a bit American. Let's go for something more Australian. So instead of Alice and Bob, we're going to have Albo and Scott. So I've got some cards here, and I asked some people to tell me who they would vote for, whether it's Albo or Scott. So we've got red cards represent Albo, and black cards represent Scott. So a ballot polling audit would involve randomizing your choice of ballots. So I'm just going to shuffle them together and let's see what we get. Random ballots. First one, looks like it's a vote for Albo. Looks like it's a vote for Albo. Oh, another vote for Albo. Oh, Scotty is in there too. You're good. Albo again. Another one for Albo. Maybe I should show the people on camera here. You're getting bored yet? Maybe we can call it. What do you think? Maybe the audit's got enough evidence to say that we probably know who won. Well, that's the sort of thing we're going to try to do. We're going to take a sample of ballots and try to get enough evidence to figure out who is the true winner. Let's put a little bit of mathematical notation here, and this is mostly for people who haven't done Stats 101. What we're doing is something called inference for a sample proportion. So we want to know what proportion of these ballots are votes for Albo. Okay, we represent that proportion by the variable P. So P is what we call a parameter. It's something that we don't know, that has a true value out there in the real world, which we're trying to estimate by doing a sample. So we've sampled some of the ballots. We're going to call those X1, X2 up to Xn. Each of those is either a vote for Albo or a vote for Scott. We're just going to assume there's no informal votes or anything. So keeping it simple. And then we just count up how many votes we have for Albo in our sample. We'll call that Y. And we can take that as a proportion of the total sample that we looked at, Y and N. And that's our estimate based on the sample of what the proportion is. And those of you who've done this before know that we know what the probability distribution is for Y. And what that means is if we were to do the audit again, question from Ian.
Sorry, Damien, is it possible to get through that?
Yes, sorry. Zoom is. Oh, can I put on the side? Sorry, was there a suggestion? Right at the bottom. It is right at the bottom. Okay, here we go. There you go. Just for now. It just says binomial distribution. So you're probably familiar with that, Ian. And here's a picture. Okay. Maybe in the bottom left corner is the best.
You can click the bottom wall.
Say again?
You can click more.
More?
Yes. And there is one option to set height.
Oh, yes. Nice. Hide floating meeting controls. Thank you. Oh, that's way better. Okay. So this is what the distribution looks like. So this is saying, if it was just to go and repeat an audit of sample size 20, what kind of things would we expect to get if the truth in this case was 60%? So in other words, if Albo truly had 60% of all the total ballots, so Albo is the true winner, this is what we would expect to get. And as you can see, sometimes we have a result that's consistent with that. Sometimes it can be quite different, even showing that Albo seems to have a minority of the votes. So that's for a small sample. And if we increase the sample, this distribution starts to get narrower and closer to the true value. So the bigger the sample, the more likely we are to get our estimate to be closer to the true value. So how close is good enough? Let's say we got 20, if we just got 13 out of 20 in favor of Albo, that's 65%. But is that enough to show that it's bigger than 50%? Well, the way we like to do it in statistics is to try to reverse that process of what that distribution looks like and come up with something called a confidence interval, which gives us sort of plausible values for the truth. So here, if we just had a sample size of 20 and we've got 13 in favor of Albo, there's quite a wide range of plausible true values out there. It could be anything from 40 to 85 would be any of those values would not be surprising. So probably can't yet conclude that we can confirm that Albo is the winner. But if we sampled more ballots, let's say we got 100, and we still got 65% in favor, now we're more certain that the evidence is actually stronger now, as conveyed by the new confidence interval, which is narrower, and is now only includes values that are clearly showing that Albo has the majority of votes. So what we want to be is in this sort of situation where we can make a clear conclusion that it's above 0.5 in this case. So this is standard inference, and we're going to be doing something like this in our for our audit. Let's just stick with this setup and what you typically learn in a statistics class, which is, okay, we're going to take a sample, and actually, if you look at the laws in this case, California, they, dating back from 1965, they said you need to run a check of 1% of ballots by hand. So they had in law at that time something like an audit. It is one of these ballot polling samples that went. It's a ballot polling study, I guess I would call it, where you do take this sample, where you get some information about whether or not the count is, whether the declared result is likely to be true or not. And it's based on a fixed sample size. The reason I don't want to call this an audit necessarily is because the law didn't actually mandate what to do next. Suppose your sample gave you clear evidence in favor of the reported winner. Well, then that's also all fine. You don't have to do anything. Suppose it did the opposite. Then you go, oh no, we've got evidence against. What do we do? The law doesn't mandate that anything actually happens. So the audit didn't have its desired effect of increasing confidence in the result. It didn't actually lead to a correction of the outcome. So yes, Ian.
Do you mind questions now?
Yeah, go ahead.
So in that case, is there any structure to what's going on here? I mean, you've got electorates building up to a total or something, or is it just sort of in a single homogeneous situation?
Good question. In practice, all those sorts of complications arise. You'll have different electorates. You might have ballot papers spread out around the place. And that does complicate the inference. For now, I'm keeping it simple. I won't discuss that, but the methods that are developed can cope with those complications.
So I was wondering this that's the law.
Yeah, I don't know much about this. This is I need Philip here to talk to this point. But I was talking to him this morning. He was making a big deal out of this, saying, yes, they didn't mandate to do anything. And one of the key things that was to put in a mandate. So the version of audits that he came up with, which I'll define later, which are called risk limiting audits, built into that definition is that something has to change the outcome if it needs changing. Like the process has to change the outcome. Otherwise, he doesn't call it an audit. So very strict.
Really specified about the manner in which the 1% sample was selected.
I don't know. I hope it's random, but laws don't always respect statistical best practice. Yeah, it's a good question, one that I would expect from a statistician. So let's develop what we want to happen. An audit's going to do something. Here are the two things we wanted to do. Either we get evidence and it looks good and we say, all right, we're going to give the election a tick, the reported outcome, or we give it a quick big question mark and say, go and check it again, which basically means doing a recount, which is quite an expensive process, but if that's what we need, then that's what we do. So those are the possible outcomes you can imagine. So you can now think about what happens, what are the possible scenarios here, what's the truth, and what's the outcome of our process. And you can get a 2x2 table. And what we want to be is on the diagonals of this table, we want to set up a procedure that's going to usually lead to a recount if the result is wrong, and usually certify if the result is correct. And we're going to try to stay away from these other two. Now, if this table looks a little familiar, it is because it is quite familiar. You can think of, there's 2x2 tables are everywhere in statistics. Here's one place where you probably first see it as a hypothesis test. So indeed, we can formalize this process as a hypothesis test, and we usually do. And in that case, we can adorn this 2x2 table with all the statistical nomenclature that comes with it. So these possible truths are called hypotheses. So we have a null hypothesis, that's what is called H0, alternative is H1. And the null hypothesis is usually the thing that we want to disprove. So we want to find evidence against it. So it's sort of we assume it until proven otherwise. So we want to have strong evidence against it. And here in this context, that means the null hypothesis is that the reported result is wrong, and we want to reject that null hypothesis. We want to find evidence to be able to reject it. And so then the two possible actions, certify and recount, correspond to what we normally would say that as rejecting the null or not rejecting the null. And we have type 1 and type 2 error, the names for the two places in the diagonal that we don't want to be. Okay, so if you're familiar with hypothesis testing, you're probably feeling pretty comfortable now. This all makes sense. Here's what those hypotheses look like for our simple 2-candidate election example. The null is that the proportion of votes in favor of the reported winner is not a majority, so it's less than or equal to a half. And the alternative is that it is a majority, so it's bigger than a half. Okay, so this is a slightly different to what you might see in the first stats course, where this will be p equals 0.5. Don't worry, p equals 0.5 is the worst case, so you can just use that and set up your procedures appropriately and it'll work out fine. But this setup is actually a bit more natural, especially when you're doing Bayesian methods. So it's actually nice to have it set up in this way. But if you're familiar with basic stats, you can just think of this as a one-sided test. Okay, we use the usual nomenclature for the probability of the different errors. So type 1 and type 2 error called alpha and beta, and that correspond to certifying incorrectly or calling a recount unnecessarily. Okay, we want to stay away from those. So you've done Stats 101. You've been brought in to help the Electoral Commission to do a election audit. So you go, okay, I know how to do one-sided hypothesis tests. So you set up your study. So I'm going to take a sample of size 1,000 because that's what I decided based on a power calculation or something. And off you go. And then you discover the election was a landslide like this. And after sampling 10 ballots, you decide you want to go home, but you're stuck because you have to sample another 990. So you wasted some effort. You could have gone home earlier because you didn't need all that much sample. Didn't need to sample that much. Or maybe you're faced with a really tight election and you get to 1,000 ballots and you still don't have enough evidence to certify. And unfortunately, you realize you should have got more. You want to stay away from these. These are both inefficient in different ways. Okay, we want something where we can just adapt to the data. We want to sample only enough to give us the decision we need. So we want to optimize or minimize the sample size, but ensuring we have sufficient evidence. So this is different to what you learn in Stats 101. This is something I only first saw in an honours year when I was studying, so master's level these days, and only for like a week. So it's nice to be coming back to that and actually applying it. And that's this idea of a sequential analysis or a sequential hypothesis test. So here, the aim is exactly what I said, which is we keep sampling, but we want to stop at some point when we have enough evidence. So this is actually a little bit more complicated to think about now. Rather than just having a statistic like y or p hat and just thinking about its sampling distribution, like those binomial distributions, and when you do a hypothesis test, you pick like a tail area and pick a critical value. Now we have to deal with a stochastic process. We have to work out, well, we've got all these random variables, we've got lots of random variables and they fluctuate. And we have to figure out, well, when do we stop? And do we draw a line here? And what does it look like? And what's the distribution of stochastic processes hitting things? So it's actually a little bit more involved than mathematics, although there are some nice, neat results, which I'll share in a second. But at least I want you to understand what this sort of looks like. These are our sample proportions over time as you get more samples. And they're quite wiggly at the start because there's a lot of variation there. That's the wide binomial distribution. And then here, it's getting narrower. So it's settling down a bit. So at some point, it's going to settle down enough that you can say, oh, it looks like we're above 0.5 now, we can stop. So that's the sort of thing. We need some procedure that's going to tell us it's not wiggling anymore and it's above 0.5. Yeah, we can stop now. So that's the sort of thing we're after. And just to set up some nomenclature, we're still going to use Y for the tally, but now it's a running tally across different samples, and same for the sample proportion. So that's those curves on the previous slide. That's P hat J. Those will appear in some formula later on. So our process is now like this. You can probably already figured it out in your head. We sample some ballots, we do a calculation, and then we need a stopping rule or decision criterion that tells us either we stop, we accept H0, or we stop and accept H1, or we haven't got enough evidence and we have to go back and sample some more. That's the sort of procedure we're after. And here's a particular procedure of that form that you would probably learn at some point in honours or master's level that we, as I mentioned, I covered briefly at the time. This is called the sequential probability ratio test. This was developed by Wald in 1945, and it's set up as follows. So you have two simple hypotheses now. So there's a particular P0 and P1. And what you do is you calculate the likelihood ratio for these two hypotheses. So here they're binomial, so they'll have this form. And that's our test statistic. And we apply thresholds on that. So we're going to have a threshold, we're going to have two thresholds actually, one for accepting H0, one for accepting H1. So if this gets too high, like if the data favor H1, it's going to start getting bigger and bigger. So we're going to accept H1 once it's big enough. Conversely, if it gets lower and lower, it's favoring H0. We're going to accept H0 if it gets low enough. And until it does that, we just keep sampling. And those thresholds depend on the alpha and beta that you want, the error rates. So you specify what type 1 and type 2 error you want, and that tells you what thresholds you need on this statistic. So it's quite a neat process. It's a simple formula and simple thresholds. And it turns out that this is the most efficient test for these two hypotheses. Most efficient meaning it gives the smallest sample size on average. So if you were to come up with another test with its own decision criteria that also controlled type 1 and type 2 error that way, it would have, you typically need more samples. So it's optimal in that sense. Although you should note that this is a very particular setting. You have to pick specific choices here. So just to illustrate how this is more useful than the traditional approach, suppose that the USA presidential election wasn't done by some crazy electoral college system, but it was instead just one big vote. So if you go back to 2008, Obama got 61% of the popular votes with millions and millions and millions of ballots. If we had to audit 1% of them by hand, we're going to be here for a while. But that's a pretty clear win. And if you were to do it by the SPRT, then you only need something like 97 ballots on average to declare it for Obama. I think I used alpha and beta as 0.05. I've forgotten now, I didn't record that. But some sets, conventional number. If you make them more stringent, you'll get like 1,000. You won't be anywhere near 1% of the votes. So this is much more efficient. So risk limiting audits. So here's the formalization of this. So we're going to use a sequential procedure and we want to give it some teeth so that it does stuff to election outcomes. So a risk limiting audit is as follows. So it's a procedure that's going to do one of two things. Either we're going to certify the election if we get enough evidence in favor, or if we don't, the procedure has to ultimately end up in a full count of the ballots. Okay. Either we just run the sampling procedure, or we can do something to make it go up there, but we have to do that. We can't just give up. Okay, so those are the requirements that we need. If you think about what properties this procedure has, it means it never changes a correct election outcome, but if the outcome is wrong, it will correct it most of the time, where how big most is depends on how much you set this parameter, which is basically your type 1 error. So here, the risk in the title refers to type 1 error, and the idea of risk limiting means we're controlling type 1 error. So that is what's giving us the most here. So we can control it really strictly, which means we're going to we'll be correcting wrong outcomes more and more often. Okay. So we've got strict control of these things, but what we don't have control of is the sample size. That's going to depend on how close the election is. So the most prominent version, method of this type was is a method called Bravo, developed by Philip and colleagues. Bravo stands for ballot polling risk limiting audits to verify outcomes. Under the hood, it's basically using the SPRT with some extra stuff to make it work in practice. In the 2-candidate election, it's basically an SPRT with the following choices. So the null value is just a half, so the worst case. The alternative value, P1, is a number you need to set, and typically you'll set it based on the reported outcome from the count, the one that's possibly adjusted a bit to make it to account for any possible slight errors. And we're going to set beta to 0, and alpha will be set to whatever you want your risk limit to be. So notice beta is 0 means that we never accept H0 until we see all the ballots. So, or to put it another way, the power is always equal to 1. Okay, we are forced to always go for the gold standard. We can't just give up some part of the way. Although we can stop sampling at any point, but at that point we just have to do a recount. Okay, so we don't have to do the expensive procedure of picking ballots at random. We can just say, well, we've seen 2,000 ballots already. It's looking like it's not, there's a mistake. We need to do a recount. You can give up and do the more efficient count of all the ballots where you just go through them sequentially, like in a proper recount. You have that option at any time, and it doesn't impact the statistical properties. The type 1 error is still controlled at the level you specify. So that's an advantage of this. That gives a lot of flexibility to the administrator who has to make decisions about how the audit's being run. So here's what that would look like. So we've got those 3 hypothetical traces before, and here is the decision boundary that you get from this method. So for a particular choice of alpha. So what you're going to do is you're going to follow your process along until it hits that boundary. Once it hits the boundary, you can stop and you can certify the election. And you just have to keep going until either you hit the boundary or until you've seen every ballot. Okay, so if the truth is somewhere above 0.5, then eventually you should hit the boundary, because this boundary, this comes out of those SPRT equations, but transform them to be this scale. This will basically asymptote to 0.5. If the truth is somewhere down here, that actually is the reported winner is not the right winner, you're never going to be near the boundary. So you'll just keep going until you've seen the ballots. Good, so you've seen the basics, something that students learn in honours or masters, applied in a specific way, and you've seen it in the context of a simple election, just 2 candidates. Let's think about more complex elections now, slightly more complex. In the UK, there's a popular style of election called first past the post. It's basically the same as what you just saw with the 2 candidates, except we've got more than 2, and we count, every voter can vote for one of the candidates, and we just pick the candidate with the most votes and declare them the winner. So here's just a hypothetical election with 4 randomly chosen names. Okay, so in this case, if these were all the votes, Albo would be declared the winner. So now we want to think about how we would audit such an election. It gets a bit more complicated now. We don't have just one parameter, P. Now we need to think about all the possibilities for different counts for 4 different, in this case, 4 different candidates. So each one will have its own parameter, proportion of votes. So a parameter space will consist of a set of vector parameters like this, where they sum up to 1. So we're now in k-dimensional space. Actually, we're in k-1 dimensional space because of this constraint. In any case, it's something that's more complicated than just a single dimensional space. In that space, what do the hypotheses look like? Well, if candidate 1 is the reported winner, then for them to win, they have to beat every other candidate. So P1 has to be bigger than PJ for all J. Otherwise, some candidate has to tie or beat that candidate. That's in order for them not to win. So the parameter space gets split into 2 parts, H0 and H1, as defined by these equations. And for first past the post, this is not such a badly behaved mathematical object. We can deal with this. We can even draw pictures. Here's a picture for 3 candidates. You can draw it because it's in 2 dimensions. And the space looks sort of like this. This is H1, this is H0. But as soon as you get more candidates, it's sort of hard to draw pictures and you have to start thinking maybe a bit more algorithmically. How are we going to deal with this? Are we going to do inference on this large space? We're going to do something a bit easier. We're going to map things down to a single dimensional problem. We're going to do that by taking pairs of candidates. We're going to take every pair such that we take a winning candidate and a losing candidate. Now, in this election, we just have one winner, but you can have elections where there's more than one winner. You can have multi-winner first past the post. That's called there's a term called plurality election, which is the larger class. In that case, there's going to be more pairs. But basically, you take every one of these pairs and you form the hypotheses of this form. So we want the winner to have more votes than the loser for every pair. And this is now just a 2-candidate problem. It's in 1-dimensional space. It's much simpler. We can use the methods we've already seen. So we can just do this, and we can do it for every pair. And we do this until we reject every null hypothesis of this form. Okay, and that's enough to verify the results statistically. Not only that, we can use the same sample of ballots to do all of those tests simultaneously. And not only that, we don't have to worry about multiple testing, which is a bit strange. You might think, well, we're doing lots of tests, then you always have to worry. Well, these tests are different to the usual multiple testing scenario. Usually we're worried about doing tests, and as soon as one of those reject a null, then we go, oh, look, we found something. Here, we need all of them to reject for us to reject the global null. So that makes a big difference. It means that the type 1 error is bounded by any one test. And that's just a straightforward probability argument, because we're looking at a set of events where they all have to happen. So we're doing one and the other and so forth. So this joint probability is always going to be smaller than a marginal probability of one of them. So that means there isn't actually multiplicity going on here in the usual sense. So we automatically get type 1 error control, no matter how many dimensions we split this up into. So even more generally, let's say we're looking at some other election. How is this going to look like? Well, it's going to look sort of similar. We're going to have an even larger parameter space. Here now, the number of things we have to keep track of is the number of possible ways that voters can vote. So every ballot type we can count and look at the proportion of. So in first past the post with 4 candidates, that's just 4 different types of votes. But when we're doing Australian elections with preferential orders and so forth, we're going to have k factorial type dimension. So this is going to be massive for Australian elections. So that's one element that's going to be tricky. We're going to have this high dimensional space, parameter space. And the other one is to actually work out how does any particular set of ballots map onto a winner. So in other words, what's the voting system like? Well, first past the post is easy. We just sort of maximize over a bunch of numbers. But Australian elections don't do that. They have a complex procedure where we move votes from one candidate to another and eliminate and so forth. So there's a more complicated function going on. So we call that function a voting rule or a social choice function. And that can get complicated. So now there's 2 ways in which things are going to get complicated in general elections, because this function is going to define what our null and alternative hypotheses look like, which is going to split up this very potentially large and complicated space into 2 parts in a way that we need to keep track of. So it can be challenging because for those 2 reasons, the high dimensionality and the complexity of the voting rule. So what can we do? I'm going to explain some strategies that allow us to nonetheless tackle lots of elections. There's a framework called Shangri-La, which is, so Philip loves these acronyms. This one stands for sets of half-average nulls, generate risk-limiting audits. So this is a general framework for creating risk-limiting audits for lots of different elections. It's general because what we do is we split the problem up into different parts that we can assemble like Lego bricks together. So we're going to split it into 2 parts that tackle the complexity of each of those 2 objects from before. So for any voting rule, we're going to define mathematical functions that we call assertions and assorters, but it basically going to map things down into one-dimensional spaces. Okay, so the challenge is going to be figuring out that mapping. Once we have that mapping, we only have to work in one-dimensional space. So we just need one generic form of hypothesis test to do all the tests, which we're going to do simultaneously in the way I've just said. So there's a canonical form for the tests. So we just need basically one or basically a small number of tests that work well on a single dimensional space. Okay, so I had some examples, but I thought I was going to run out of time. So I can show you later if there's more time, but to just give you some examples of what these look like. But the basic idea is we're going to map things down into one-dimensional space where we're now doing an inference for a random variable in that space. And the inference is going to look like this. We're going to look at the mean of a random variable, and it's going to be a non-negative random variable. So it can have value 0 or higher. And we're going to test whether its mean is less than or equal to half versus greater than a half. So those functions, these assertions and assorters, are designed so that this is the hypothesis we need to test. If this looks familiar, it was intentional. It's meant to mimic the intuition for doing a two-candidate test like we saw before. So we just but now instead of having just a proportion here, we have a more general random variable that can be bigger than 1. So it's not just a number that's bounded between 0 and 1. It's bounded below by 0, but it can be higher than 1. But we're still testing whether its mean is less than or equal to a half. So we just need a distribution-free test to cope with the general random variables that we can chuck in here. Can we do that? Indeed, we can. The strategy that's been used to come up with tests for this relies on objects called martingales. So these come up a lot in probability theory. I won't go into the details of what they are. Again, this is something you can ask me about over dinner if you like. But they are well studied, and there's some really useful theory about them, which is that you can bound how far or how high these numbers get in a way that lets you construct a test that controls type 1 error. Okay, so what we need to do is construct one of these martingales, and then we can use it by calculating. So the martingale here would be basically a statistic. It's something we can calculate from the data. And we know that if we set this threshold, so if we reject when that number gets bigger than 1 on alpha, by the martingale theory, we know that this limits type 1 error. So we can use this for no matter what variables come in, as long as the function we devised here we can prove is a martingale. So there's a bunch of different functions that we've come up with, or rather Philip and colleagues have come up with. Here are some the older ones that they've used in their software. These are surpassed now. Here's the latest one that Philip is keen on, that he just developed recently. I won't go through the details. Basically, it's just a function of the data that satisfies those martingale properties and lets you carry out that test. If you want to know more, Philip is doing a short course in about 2 weeks. It'll be online, so you'll be able to join in. We haven't quite finalized the dates, but if you're interested, contact me or look out for an announcement, and you can learn a lot more about these methods that will allow you to do non-parametric inference in general settings. Back to Ian's question, the real world is messy. All sorts of stuff happens. People don't vote. They're putting blank papers. Papers go missing. In the US, there's more than one contest on a ballot, and not every one of those will get filled in. So stuff like that can happen, but maybe we need to do some stratified sampling because the ballot papers are all over the place. And I mentioned there's other types of audits. There's something called a comparison audit, which involves comparing against a digitized record of the ballots, sort of like a paired test. These are more efficient usually. So if we have that extra information, we can use that. All of these complications are ones that can be handled with the Shangri-La framework by adapting those assertions and assorters in the right way. So if you can do a ballot polling audit in Shangri-La, you can automatically do a comparison audit too. So it's quite a powerful framework. Here is Philip and Ron actually carrying out an audit. You can tell that they're doing things seriously because they're generating random numbers using these magic dice here that Ron brings with him to make sure that we do really get truly random numbers. Here's a stack of ballot papers. They're all numbered so that they can get retrieved based on the sampling schedule. So yes, these things are actually being used in the US. Most of them, mostly in a pilot, a pilot sense, so they're not running real audits that have the teeth to change an election, but they've been tried out in many, many states. If Philip were here, he could talk a lot more about which states are doing it and which ones aren't and so forth. But we're more interested in Australian elections. So let's talk about what we do here. So I'm sure most of you are familiar or will soon be familiar with what these ballot papers look like. So in Australia, we vote using a system where we have to rank the candidates. So we get a ballot paper like this and we put the numbers 1, 2, 3, 4, in this case up to 8, in order of preference. And then there's a complicated process to count these. I'll quickly go through an example, but before I do that, I just want to introduce the nomenclature that's used in the field here. The type of system we use for the Senate, for the House of Representatives, which is what this ballot paper is from, is called instant runoff voting. And the type of system we use for the Senate, which is similar but it's got more details, it's called a single transferable vote. So these are the terms used in the the academic literature on the study of these things. We use these systems throughout Australia in the federal level and also in the states. And there are slight differences from one state to another. So you need to be mindful of these if you're often, because if you might need to adapt your method to suit. So here's a very quick run through of what a Senate count, so an STV count looks like. We start off with ballots. So here are possible ballots we might see. And this one, and these are partially completed. So here we've put candidate 1 as the first preference and candidate 3 as the second preference. And there's 8,001 ballots of that type. Here, these are votes only for candidate 1 and no other marks on the ballot paper. There's 1,000 of those and so forth. So the way the count works at a high level is we count all the first preferences, so sort of like first past the post, and we look at the totals for each candidate. If any of those counts surpass a number called a quota, then they get elected. And the excess votes above the quota get redistributed to other candidates in proportion to the second preference votes. So there's a reduction in values, what we call a transfer value. So we start moving votes around and we start multiplying them by a weight factor. And we keep doing that until we get to a stage where no one's votes surpass the quota. And at that point, we eliminate the candidate with the smallest number of votes and redistribute theirs according to the next preference. And we keep doing this until we elect the number of candidates we need. So in this case, we have 2 seats to fill. So we keep going until we elect two candidates. The main reason I'm showing you this is to illustrate that this process is involved and lots of things can happen and lots of weirdness can happen is when one candidate just surpasses another. So suppose there's an error somewhere along the line. Suppose there's an error on one of the counts and that means that 2 candidates swap places at a key moment. The outcome can be quite different. So this is part of the complexity of Senate elections. So can we audit these sorts of elections? So for IRV, which is the system used for House of Representatives, I should say the main difference between this and the House of Representatives system, the IRV, is that we don't have this transfer step. We only have elimination steps. So we don't get fractional votes. We have integer counts. So it's a bit easier to to reason about those counts. And for that reason, we've actually so Michelle, Peter, and Vanessa have come up with a way to audit that system, all those elections, by using the Shangri-La framework. They managed to work out assertions and assorters, which are, remember those mathematical functions, that map this down onto one-dimensional space and allow us to then run an audit for this election. And there's some complex optimization going on under the hood. And I won't go into the details there. It's something we can chat about over dinner if you like. And I actually ran a pilot of this in San Francisco in 2019. What about the Senate? The Senate got the extra complexity with the transfer value. This is still an unsolved problem. It's one that we're working on. And we've got a few ideas for how we're going to tackle it. One of them is to try to develop those assertions and assorters for STV. It's going to be more complicated than for IRV. But that's one approach, if we can do that. Another approach is to develop what's called a Bayesian audit. Now, I haven't talked about a Bayesian approach here, but there are natural Bayesian approaches to doing inference here, and you can apply them. And the main challenge then is to show that it's risk limiting. So that's another approach we could try. And another one is to develop martingales that are specifically tailored towards these elections. We've got ideas for how to tackle it in all of those three ways. We have actually made some progress. We've developed an assertion-based method that can audit an STV election that only has 2 seats. That's good. That means we can audit elections in Canberra and Northern Territory, so ACT and Northern Territory, but the other states elect 6 seats, so we can't quite do that yet. We're also using these other 2 strategies using what's called a Dirichlet tree model. Very briefly, Dirichlet trees are sort of like a Dirichlet distribution, but with some extra structure, like a Dirichlet distribution that are conjugate to multinomial. So you retain the nice computational and theoretical properties, but you get the extra power that you can split up your space in a structured way, which lets you cope with higher dimensionality much more easily, which is what we need because we have K factorial style dimensionality here. So our trees will look sort of like this. The type of trees that we're exploring are ones where the splits correspond to preference ordering. So the first split is based on the proportion of different first preference orders, and then conditional on that, the next preferences and so forth. So we can split up the whole parameter space in this hierarchical way, in a way that's going to be computationally feasible to do Bayesian inference. Well, that's the goal, and we're partway there. Lastly, I want to just mention that bill that was passed last year. So it's called the Assurance of Senate Counting Bill. And if you read it, it says basically that the Electoral Commission has to do a statistically significant sample of ballot papers to check yada, 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 to check that the electronic data reflects the data recorded on the ballot papers. So it requires them to check that the digitization step records the data faithfully. And they have to do at least 5,000 ballots. Now, they don't define what statistically significant means, nor do they define what kind of errors that need to be checked. But at least something's going to happen. So hopefully it's progress. You can help us make progress. We've just recently got a grant for this work. There's a postdoc position available. It's currently open. The application's deadline is next week. So we'd love to hear from someone who wants to join us on this journey and develop some auditing techniques for Australian elections. Also, we have PhD options available, including a generous top-up scholarship. So get in touch if you want to join the team. Thank you very much.
Very nice talk, Damien. I was actually teaching yesterday election data, so that was really interesting. So we do have a question from online from Rob. Actually, you touched a little bit on this, and just making sure they can hear me online.
Yep.
So about under the complications. So Rob's question is that you're kind of assuming simple random sampling. So how would you extend it in a real case where essentially ballots come from different polls? And so you're getting clusters of the counts.
Well, you want to be able to sample individual ballots rather than doing cluster sampling, but you can do stratified sampling. So you would do that, for example, mainly for logistical reasons. Like if you've got a workforce if you've got multiple electorates, So they've each got their own set of ballots. You want to be able to sample from all of them, but maybe you want to spread the workload out a bit. So you can actually specify in the Shangri-La framework sort of assertions that will let you do the right thing statistically. So I know that doesn't completely answer your question, but you can cope with stratified sampling using the framework that's already there.
Yep. Question for Modis. Damien,
Yes.
you could repeat the question.
Yes. Tim.
So I have two questions. The interesting one is probably the legal one. I know the High Court has real problems with anything to do with elections, which involves anything to do with statistics. Because in the 2013 case where ballots went missing, they ruled that under the Constitution of Australia, anything to do with statistics and elections was foreign. So do you know if anybody's checked whether this law that has been passed with statistics in it is going to survive after challenge?
Yes, so I'll repeat the question. I might summarize it. Tim Brown has asked whether, basically, how is the court, especially the High Court, going to cope with this law? Because the High Court seems to be a bit allergic to things that involve statistics. Very good question, Tim. I don't really know the answer to that. The law's there, so someone, I guess they'll have to, if there's a case, they're going to interpret it, and I don't know how they'll interpret it. I guess this is a question for someone with some legal experience here. Sounds like you've got a bit more legal experience than most of us in the room. I guess the hope is that the law will just spur the parties to do the right thing, and there's no legal cases. But yeah, I don't know how a court would interpret any case that's going to be involving that law. I'm interested in how the AEC is going to interpret anything to do with statistics as well, so let alone the High Court.
So the second question is, you mentioned those that Martingale inequality, and I haven't heard it described as real inequality. That's not the question. But there are a lot of inequalities of that kind of form. Is it possible that there are other Martingale inequalities that can generate?
Yeah, so the question was about the Martingale inequalities. So Tim's noted that there are other similar looking inequalities. And indeed there are, and I often get confused, and I was trying to look them up to make sure I got the right one.
Right.
And they're all named after, well, mainly Russian statisticians. I guess Beale probably French, but so yeah, I get them all confused. They are quite related to each other. I think you can use many of them. So some of the older martingales I showed were based on some of the other inequalities. So yeah, you can use any of those because they're all about bounding how far, what the probability of going far away. So that's the sort of bound we need. So yeah, any of those inequalities that do that can be used as a tool to develop a statistic to use that's going to control type 1 error. You happy for me to die?
Different question. Another issue related to elections, and you hear a lot about in the US about gerrymandering, but it is an issue actually here in Australia as well, and that affects election results. Gerrymandering in Australia, you expect that your electorates have the same number of people. So this is one of the sort of hidden things in your work, and it's not true actually. And it's not true to the extent of 2 to 1 in the extremes. And some of it you can imagine that it's Tasmania, can't split Tasmania and Victoria, for example, they're separate. Or we've got big open spaces out in most of Australia. And so you maybe don't want to have a gigantic big electorate, you might make it really big, but still not that big to keep the population. The population might be smaller in that one because land is so big. But it's not actually true. That's not where the big differences in the population are. It's in the smaller inner city areas. And that suggests political interference. So anyway, so side comment, but it's something that will be interesting to.
Yes, so yeah, just to summarize, I was commenting that gerrymandering is an issue and can lead to basically a bias in who the elected representatives are as compared to the will of the people in some more general sense. Yes, indeed, that's true. In terms of auditing, it's sort of a separate thing because we just take the ballots as given. Like we're looking at what the ballot papers are, but gerrymandering will mean that what's on the ballots is skewed towards one party or another. Yes. So yeah, it's an issue that's important to be worried about if you're worried about political and then electoral integrity. Ian.
I think my question is related to Rob's actually, but even within an electorate, they count it by polling booths, and the big differences between the fraction voting for a particular candidate and the polling booths. And so you've already got even quite a complex stratified structure there within one electorate, let alone across electorates. So I sort of see that as a big challenge. I mean, maybe you can do it with stratified sampling, but can I just follow on one more practical thing? I'm struck by the photo you showed. Years ago, I was involved in trying to sample beer bottles from a massive collection in a warehouse that was stacked on pallets. And the dimensions of the pallets, like, 30 pallets this way and 50 that way, and I'm stacked about 10 pallets high. I said, contemplate a simple random sample from that. You want to get a pallet in the middle. Forget it. Well, I'm looking at that now. So what practically happens when they want a ballot from the box, from the second pile to the right? And I think there's lots of scope for things to go wrong. Practically, I don't know how to deal with such things, but you go to the election officials saying, forget that ballot, just take the top box.
Yes. Yes, Ian's wondering what happens if you have to sample from box number 411221. Do you get some strong person to come here and list all the boxes, or do you just be lazy and pick one from the top? Great question. I don't actually know what's going on here. I don't know if those boxes are empty or not. Presumably they're not. But I know that Philip and Ron, more than anyone else, care about integrity. So I think they'll get pretty strong by the end of the night there.
Yeah, I'm just saying, I anticipate them running to.
Yes. So
Injections and lots of
yes. So you'll need to make the process practically straightforward to not have those barriers. To not have to lift lots of boxes out of the way to get to the one you really need. Yes, those are important practical considerations. And there's other ones along those lines that are similar, which is about keeping the calculations straightforward enough so that people can verify it and know that it's been done properly, and using software that's open source. And like there's all manner of these things. The statistics ends up being a very small component in that, but it's an important bit, but there's lots of other important bits too to make it all result in a trustworthy process. Lauren.
I guess it's really important to discuss something, but if it is to kind of detect an error that's sufficient to change the outcome of the election, rather than to detect errors, right? Because you would want to take into account cluster something if you're looking for the dodgy groups or whatever, the machine that was malfunctioning or whatever. But maybe not when you're thinking about that, there's no sense of that. Is this all that you're voting that will change the rules? Is that kind of the idea? That's one question. I'm sorry.
So let me see if I got it. You're wondering whether, when we do this inference, our aim is mainly to just work out what the outcome is, and small errors might not change that. So we might not need to worry about it as much. So we don't need to track down every single error necessarily and learn about it. And also that means we might not have to worry as much about the impacts of stratified sampling, for example. The answer to your broader question is yes, we only care about verifying the reported outcome. So small errors will not make a difference there. So even if the main count had errors, but it was small, and a ballot polling audit might still confirm the winning candidate is the true winner, because they are, even though there were some errors. So yeah, small errors might not matter, and the procedures that we've developed here allow those to come in and not impact you. If you wanted to understand the nature of the errors, though, that's a different kettle of fish. Then you have to definitely have to do much greater study with more detail and find out where the errors are coming from. But that's not the point of an audit. Now, how many more questions are we allowed? Okay, last question.
I just wanted to, like, I don't know if you, a few years ago, there was an election in Victoria where the result changed multiple times through the recounts. They had, like, I think 3 recounts. It was a seat of Jake Jager in Northern Melbourne. And like they literally changed by 1,000-ish votes each time. Like, so it was like a margin of 400 and something again, I think. But every time we flipped by about 1,000 votes. And so, but the problem was that the arguments weren't anything to do with the actual counting of the votes, but it was what counted as a valid vote and what didn't. So does that factor into what you do?
Indeed, that's important that we know how to interpret the ballots. So let me repeat the question. Paul mentioned that there was an election in Victoria recently where there was multiple recounts, maybe a while ago, and where the recounts ended up with very different results each time. And the reason was mainly to do with arguments about whether a vote was or wasn't formal, or wasn't valid. Yes, I think those sort of arguments are always with us and we can't make them go away. And that's just part of the error in the process that we have to live with. And I suspect the answer is if that source of error is so big that we can't settle on a clear winner, we may end up just having to rerun the election or something, like if it gets that bad, or one particular person's interpretation or groups, whatever, might have to be declared to be the official one. I don't see any better resolution than that, unfortunately. But someone who's thought more about this may have better ideas. But yeah, statistics won't magically fix the problem of interpreting ballot papers. That's a human judgment problem. So we live with that.
Okay, well, thank you, everyone.